Welcome back, everybody. So this is the example where we find the expectation of not a variable but a function of that variable. So let's say we have the PDF f of x of a variable x, and we want to find the expectation of y, where y is a function of x given by e to the x. In the previous example, we found the expectation of x, if you recall, and so here we want to find the expectation of e to the x, not x. Before I begin, I want to point out that if notice that the probability, the PDF is 0 unless x is between 0 and 1, and so if you look at when x is between 0 and 1, then the y, which is e to the 0, which is e to the x, would be between 1 and e, because if x is between 0 and 1, y would be between e to the 0 and e to the 1, so y would be between 1 and e. So the PDF of y would also be 0 outside of this range from 1 to e. Now, one way to answer this question is to first find the PDF of y. So how do we find the PDF of y? Well, if you recall, in one of the examples we did something similar, so where we first found the CDF and then we took the derivative. So let's look at the CDF of y. The CDF of y evaluated at y would be the probability that y is less than or equal to y, and that's the same as the probability that e to the x is less than y, because e to the x is equal to cap y. And this inequality right here, if we take the logarithm on both sides, then we get that this is the probability that x is less than so this is the natural log. Maybe I should have written ln. So this is the natural log of y, and so then we find that the CDF of y evaluated at y is the same as the CDF of x evaluated at log of y. Okay, so now to find the PDF of y, we just take the derivative. So the derivative on the left here would be the PDF of y, and on the right hand side we take, by chain rule, we get 1 over y times remember the derivative of the CDF of x is the PDF of x, so you get 1 over y fx of log of y. So this is our PDF of the variable y. So now the expectation. So the expectation of y, it would be the integral from negative infinity to positive infinity, y times the PDF of y evaluated at y dy. Now the PDF is here, we just calculated that to be 1 over y fx of log y dy, and then we get fx of log y dy. Now, what we need to realize is that if you recall that the fx, the PDF of x is 0 unless x is between 0 and 1. So right here, the input of log y, unless it is between 0 and 1, this integrand would be 0. So if log y is required to be between 0 and 1, then y would have to be between 1 and e. So what we find is that unless y is between 1 and e, this integrand would be 0. So we go from 1 to e, and in which case this value would be 1, and then the value of the integral would be e minus 1. So again, that's because so this improper integral outside of the range from 1 to e, this log of y would be outside of this range, and in which case the PDF of x would be 0, as you can see here. The PDF is 0 unless x is between 0 and 1. So that's why in the integral here we require log of y to be between 0 and 1, which means that y have to be between 1 and e, in which case the PDF value is 1. Alright, so then we get e minus 1 as the expected value of y. So this is when we found, so to find the expectation of y, we first found the PDF of y, and then we used the definition of the expectation. There's a little bit easier way of doing it, which is to find the expectation of I have a typo here. So to find the expectation of e to the x, we just take the integral from negative infinity to infinity of e to the x times f of x dx, and because f of x is 0 unless x is between 0 and 1, this integral reduces to the integral from 0 to 1 e to the x dx, and that's just going to give us e minus 1 again. And so this is much easier than what we have done to find the expected value of y, which was e to the x. So this follows from this fact that given a continuous random variable x and its PDF f of x, if y is a function g of x, then the expected value of y, or the expected value of g of x, is the integral from negative infinity to infinity of g of x times f of x dx. So whatever the function of x is, you just multiply that by the PDF of x and integrate. So as a consequence of this is that the expectation of ax plus b, where a and b are constants, is equal to a times the expected value of x plus b. And this follows because if you look at the left hand side, the expected value of ax plus b would be the integral from negative infinity to infinity of ax plus b times f of x dx, and then we can break up this integral into two integrals. So we get a times the integral from negative infinity to positive infinity x f of x dx plus b times the integral from negative infinity to infinity of f of x dx, and which is exactly the right hand side, because the second integral here is just 1, because that's just the total probability. Okay, so that's the end of for our discussion on expectation. In the next video we will define variance.